So I think this lesson is a little easier than the last one.
Let's hope.
Because we should already know, what does an integral represent? Like if I just said, what does the
Area under the curve.
The area under the curve. So when I do from here,
Mine was a correct answer. Just for
this equals, that's the derivative.
The derivative. Oh, girl. I thought they all did something. Oh, girl.
Right? So this is going to be
the opposite. That's okay.
area under the curve of a function. Now, if it was just the integral of f of x, we would stop when we get to the x-axis. Now we know whenever it goes below the x-axis, what happens to the area or the integral? Negative. It becomes negative. So what happens now if we want to contain the area between two functions? Well, we're going to take this area and we're going to subtract the lower curve. And that's going to give us the total area between the upper curve. So we're going to take the upper curve minus the lower. And our limits of integration are all going to be in terms of x.
Why would we subtract it?
Okay, well, let's think about that for a minute. What if I were to take, what if I took a function? Let's say f of x equals x squared minus 4. Right? Just a quick sketch. And I said, okay, so this is negative 2 to 2. And I said, what would be the integral from negative 2 to 2 of x squared minus 4? Now, I don't need you to actually figure it out. But what's going to happen with that? You're going to get a negative number, right? Because between negative 2 and 2, it all goes below the x-axis. Now, what if I said, what's the actual area that's bounded? What would I have to do? Is essentially what I'm going to do is I'm going to take 0 minus that to make it a positive number. I'm basically saying, okay, take this minus this to get the opposite, which will make it a positive value. Okay, so it doesn't matter if the whole curve, whatever, like if, that was a bad picture.
That was a great picture.
It doesn't matter if the whole, now I'm using the highlighter, if the whole curve is below, like if this is f of x and g of x, how will that work? Well, we'll take f of x, which would go all the way from here to here, minus g of x that goes from here to here, and then left over with just the region between the two curves. Okay.
Oh, so basically we're like lifting it up.
Yeah, I mean, it doesn't matter if they're both below the x-axis, one's above, one goes below. It will always work out. Okay, so let's look at an example. Find the area of the region between y equals x squared plus 6 and y equals x. So this is y equals negative x squared plus 6 on the top. And on the bottom, we have y equals x. So we want to integrate this. I gave you the limits of integration from negative 3 to 2. And we're going to use, just to save time, especially just with the lesson, because we've already done a lot of these integrals, we're going to use our calculators. So we're going to do, which one is on the top? Which is the upper curve?
The y equals negative x.
Good. So I'm going to have negative x squared plus 6 minus the lower curve. Okay, so let's go to
the new graph has the same area as that.
Yeah, exactly. So if I were to graph this, it would be a parabola. And if I found the area under the curve of that area in the x-axis, it would be the same area between the two curves. Everything okay? Good.
Oh, I forgot to charge mine.
20.833. Good? again, we could have done this by hand. It's fine. We'll just, again, save some time. Now, what happens if I end up with a negative number? You're wrong. Most likely, when you get a negative answer, you probably switched something around. Okay? Therefore, you are wrong.
Wait, so
As
it's 20.8.
Sophia says. 833. Okay, now find the area between the region, y equals secant squared, and sine x from 0 to pi over 4. So it's not necessarily where they intersect. I'm just going to restrict it on that domain. So we're going to put from 0 to pi over 4. What's on the top? Secant squared of x minus the bottom.
So you just put that into the
Yeah.
calculator.
Of course, if we needed to do this by hand, the integral of secant squared would be tangent. Integral of sine would be negative cosine, so that would make it. So you could evaluate this by hand, but so on the take-home quiz that I'm going to give tomorrow, I am going to ask you to work things out by hand, but it's all calculator okay, so you'd be able to check your answers afterwards. Yes, Owen.
It's like not letting me do
What? What do you mean it's not letting you do secant?
Let's do it out.
Is your calculator in test mode?
Oh, it's on the east.
It's in test mode.
Oh, how do I take it out?
Anybody else get the answer yet?
0.7.
Yeah, I think it's a pretty small number.
It's telling me I'm missing a parentheses.
You're missing parentheses.
You put the square next to the secant instead of after the x. It'll
I'm
tell you that.
helping you.
I made that mistake before.
Did we get it?
Dude, what is happening? I'll try again.
Wait, what did we get? Point what?
707.
0.707?
Yeah, I don't know what I'm on.
Anybody else?
Wait, is that wrong? Hold
See,
on.
Harrison's busy doing something else.
I actually did get 0.707.
0.707?
I probably
0.780064. What?
Whoa.
Are you in degrees or radians?
Oh my god, girl.
Okay.
She's in degrees.
English almost dead.
I've literally what? Oh.
Poor Imbal, she's like struggling.
Just.
Or what if I go to BC? Or what if I go to Coast and enjoy?
For what?
Okay.
Why is it so casual though?
Yes, 0.707.
You don't get it.
Okay, let's do the next one.
In New York.
No, I know what
That's
you
true.
mean.
Okay, so so what does y equals 2 minus x squared look like? It's a negative x squared plus 2. So it's going to go here. So like this. And y equals negative x, which is going to look like this. So we are trying to find this area. Okay, so we need to find the limits of integration before we can we can integrate, but we want to find out where do they intersect. Now, I graphed this very nicely, but what if you didn't graph your parabola as accurately? Well, we want to see where they're equal to each other. So if I were to set them equal to each other, I have a quadratic, which factors very nicely to get x equals 2 and negative 1.
Wait.
So where do they intersect? This intersects at negative 1, 1.
But why do we find that?
And this is
In case you don't have an easy graph to graph, you know.
yeah, so we're going to do some on our calculator where it doesn't work out nicely. But I need to use
Oh, because that's the limit.
yeah, those are
Oh,
so I'm going to take the x
I
coordinate.
understand
Now, I put the y coordinates in here. The y coordinates we don't need. We don't need those just yet. So for right now, I'm going to take -1 to 2. And which graph is on the top?
That's good.
2 minus x squared minus negative x. That's going to make it plus x. Yes, Owen.
Wait, can't you go like beyond 11?
So what is the directions? Find the area of the region enclosed by the parabola and the line. Now, that's not to say I couldn't find areas beyond that, but if I specifically ask for the area enclosed, that's why that is important there. And what do we get for the answer here? Now you have your calculator. 4.5. Excellent.
How is it such a nice answer?
Isn't that so nice? It is.
Not always.
Okay, it's not always and maybe not on the next one.
4.5.
4.5 is correct.
The next one seems like it would be even.
Okay.
It's telling us it's really not.
Oh goodness, what is this?
All right. Find the area of the region enclosed by the graphs of 2 cosine x and x squared minus 1. Which one is on the top? The cosine x. The 2 cosine x. And the one on the bottom is the x squared minus 1.
Why is it?
Because x squared minus 1 would be a parabola.
And this one's like the
Right? Remember, cosine always starts here at 1.
Yeah, okay, wait. I thought you were talking about the wrong one when you were talking about the top one. Yeah, I confused
You got
myself.
it, you got
I
it.
know what the graphs look like. I don't even know.
Okay, so now I have to figure out where these intersect. So I'm trying to figure out where 2 cosine x is equal to x squared minus 1. So I could set it all equal to 0 and look for the zeros, or I can graph each of them and look for the intersections. Okay, I'm going to pause the graph. I'm just going to graph them separate. So I'm going to put 2 cosine of x, graph that, tab, and then I'm going to put x squared minus 1, enter. You can change it if you want to change the viewing window. You don't really need to, but you see how that's the shape that we have here? Just kind of zoom out. Okay. So I want to show you how to store intersection points because we want to have as much, we don't want to wrap around. So let's find the intersection on the left. So I'm going to go to menu. We're going to analyze graph. We're going to look for intersection. Okay, so do you see this intersection here, -1.265? Here's what I want you to do. I want you to click on the x coordinate. I want to store this as a variable though. Okay, so we're going to click control variable. So do you see above it, it says store? So I'm going to do control variable and just pick a letter. I'm going to pick A, but.
I'm going to pick A too.
Okay, after you click A, sorry, I'm having technical difficulty. Press enter, and it should become bold.
It's bold.
Yay! So now anytime we click the letter A, that number is going to be there. Go do the next intersection. So repeat the process.
The next one's just -8.
Yeah, I know. But it's not always going to be that way. So go ahead and do the intersection.
Well, click.
You click on it.
Yeah, click on it. Now press Control Variable.
Control. Where's variable?
VAR.
Oh.
And
Oh.
yay! So you stored each one. As soon as you store it, let's make the other one B. Because I want here, this is how I'm going to write it. I'm going to put A and B here. And I'm going to put A is equal to negative 1.265 and B is positive 1.265. And then I'm just going to put in 2 cosine x minus the parabola dx. Okay, so let me just do this again real quickly. Analyze graph, intersection, here, select it, control variable B, enter. Okay.
How do I delete a variable? Because I accidentally saved the wrong thing.
You can't, you'd have to like clear your calculator. You don't need to. Just save it as a new one. Okay, so here's what I'm going to do. I'm going to type in A to B. Oops. So I'm going to put in, what did I store? I stored A as my lower limit of integration, B. So you should get these nice little bold letters. And I am going to just type in F1 of X. Because remember, I already have it stored. How'd you lose it? No, it's if you turn off your calculator, everything should still be there. Why'd you clear it? Now, in a problem like this, it probably is just as easy to just type in the actual functions. But sometimes we get really complicated functions that we're working with. So you can just type in, you just literally type F1 parentheses F minus F2, and we press enter, and that should give us our answer.
I got like almost 5.
Yep, 4.995. Okay. Something is happening with my computer.
That's so cool. Oh my gosh.
I knew this.
You knew this?
Yeah.
Okay.
I think I tried it one time because I was too lazy to figure out function.
Yeah,
They
they
were
were doing that.
All right. Good. All right. Now let's look at boundaries with changing functions, which I'll explain. So here we have an area that is bounded above by y equals square root of x. So this is our y equals square root of x. And it's below by the x-axis, which happens to be here at y equals 0. And over here by the line y equals x minus 2. So we have a situation where the upper curve is always square root of x, but the lower bound is going to change. So what we need to do is we're going to write 2 separate integrals. Okay, so the first one, and we're going to split it up right here where it changes. So the first integral is going to go from 0 to, what x value did it switch over to? Of the square root of x minus 0, so we don't really need that minus 0. And now we want to look at this region, so that's going to go from 2 to 4 of the square root of x minus the x minus 2. Again, you can distribute the negative. It's okay if you just set it up like that. Are we okay with that? All right, this turns out to be, let's see. Oh, okay, for the first one. Okay, so when we add those together, 3.3 repeating.
Yeah.
You should get 3.333 repeating.
What's this? 4.
Double check.
No, 3.3.
Oh, did you round your previous answers? Don't round your previous answers. Did you actually select the previous answer?
Yay!
Should be 3. I'll look.
When I get it right,
It's so nice, isn't it? Okay, so there's actually an easier way to evaluate this, which is what we're going to look at on the next page.
Easy,
I know, isn't this fun?
Oh, I actually enjoyed this lesson.
Right? So we can integrate with respect to x, and we can also integrate with respect to y. Yeah, you can. You can delete them. It's just more work. You don't.
No, it was simple. It was 2 steps.
Okay, so let's say we have 2 functions and they're in terms of y. So we're not going to do the upper curve minus the lower curve. We are going to do the right minus the left. Just think it's the one that's further to the right here. And C and D are y coordinates. So just keep in mind where they intersect. C and D, these are y values. So everything, all the problems that we did on the previous page, everything was in terms of x, including the x coordinates. Now everything is in terms of y. So let's take a look at this last problem again. But let's see if we can do everything in terms of y, and we can make it one integral.
Wait, I don't understand. Are you gonna tell us how to do it right now, or you already did? Okay, because
We haven't done this yet. Okay, so this one, my limits of integration are going to go, so I'm starting off here at 0. So it's going to go 0 to 2, because if we look where they intersected at 4, 2, we just want to use the 2. Now, I want to figure out what is on the right and what's on the left. Well, on the right is that red line, x minus 2. But I want to solve for y. I need to have solve for x. I need to have everything in terms of y. So I'm going to rewrite this as y plus 2. So I'm going to take y plus 2, and I'm going to subtract. Yeah, but we don't need to worry about just the plus, because my lower limit of integration is 0. So I'm not including that portion of the graph anyway.
Wait, but why is it from 0 to 2?
Because what's my y value here?
0.
What's my y value here?
Oh! Okay.
Okay. So
what about the 0?
Which 0?
The y equals 0 down there.
Here? Well, where am I starting?
The line, yeah, that line.
Yeah. What's my y value there?
0. So there's just no change. We don't care about that the bottom 2 are 2 different graphs.
Wait, look at it
Correct.
like this.
Well, of course you get the same thing, right?
Then it's just from 0 to 2, and it's like that.
Look at it like what?
Like, hold your paper
Yes, if
sideways.
you flip it around.
Oh yeah.
So if you
I
flip
get
the whole
it.
thing,
Okay.
it's the same idea, just
Okay. Gotcha.
exactly.
So
If
it's
we rotate our
straight
paper,
horizontal.
it's the same thing as top minus bottom. Yes?
Mhm.
Okay.
Wait, I didn't write that down.
Oh, okay, here. We only have one more example.
So is y equals x cubed, right?
Okay, you're good.
Okay. Yeah, which one is y equals x cubed? It's the one on the right. And here, this one on the left is x equals y squared minus 2. Okay, so the one on the right, instead of y equals x cubed, if I solved for x, that would be, good, it would be cube root of y minus the y squared minus 2. Again, you could do minus y squared plus 2 dy. Are we okay with that? Right minus left.
Oh, also, we're only doing the section where they're between their intersections.
Mm-hmm. Okay, so that means I have to find these two intersection points. Now, I could set them equal to each other, or we could do it in the graph. Now, if I did it in the graph, how would I create that? How would I type this in?
Type what?
How would I type these two graphs? So I have y equals x cubed. Okay, so there's my x cubed. I think I'm gonna go back to standard.
X plus 2.
Oops. Okay, so what happens in the second equation? If I change this to y squared equals x plus 2, I would have plus or minus the square root of x plus 2. Because if you, right, the sideways parabola?
Yeah.
Okay. So I'm going to put this in. So I'm going to have the square root of x plus 2. Graph that. And then I'm going to do the negative square root of x plus 2. Okay, so now we have our lovely graph here.
Oh wait, why can't we have it as one graph?
Yeah, just write plus or minus.
Oh, no.
That would not be a function.
It wouldn't be a function.
Or in the graph.
So we can only.
But you would have to
graph
put it in as a
functions.
relation. Okay?
Okay, so what is the intersection?
So let's find the intersections.
Wait, is it?
Wait a minute.
I'm waiting a minute. How did I get what?
Why is your thing? Oh, you just did 3 graphs. I see.
I did 3 graphs because technically.
Yeah. got
Now,
it.
this is not the only way to do it. You could put everything in terms of x, but then you would just look for the y coordinate, or you would look for the x coordinates. So this is going to go from -1 to, I have that as b. So b is equal to mine. So sometimes if you already have like the intersection stored, when you put in new graphs, it will automatically create a new intersection point for you. And it's already linked. Now, oh, you know what? Actually, let me.
Yeah.
And so just plug that in. We should get 4.215.